Alright, let's take a look at sketching another example of a whole found in a rational function. So here we can actually notice that the degree of the denominator is 1 higher than the degree of the numerator. If I factor this, let's use a different color here. So if I factor this, f of x, x minus 2, if I factor the denominator, we get x minus 4 times x minus 2, right? And you can use the decomposition method, two numbers that add up to -6 that multiply to positive 8. Excuse me. And that can be negative 4x minus 2x plus 8. If I factor this out, you get x minus 4. If I factor out negative 2, you get x minus 4, and you get x minus 2 times x minus 4. Okay, so we understand that. Now, the next thing we want to do here is we can notice that there is a common factor, so we can cancel out the x minus 2. We can understand that f of 2 here would give us 0 over 0. This indicates an indeterminate state. Indeterminate states will indicate that there is the presence of a whole, right? So if we have a common factor, then we have a presence of a whole. Now the function that we're actually going to be working with is going to be f of x is equal to 1 over x minus 4. Okay, so it's going to basically be a reciprocal function. And if I wanted to analyze the domain range here, the domain excuse me, the domain here is x belongs to all real numbers, but x cannot equal 4. Okay, so x cannot equal 4. The range here, right, we have to, so this is our simplified expression, right, but we can also understand that x cannot equal 2 as well, right? So just because we cancel out doesn't mean we don't have to list it. As currently our domain here, x cannot equal 4, but we can also understand that f of 2 would give us 0 of 0, so x cannot equal 2. Now, looking at this is our simplified expression, so this is the function that we're going to be working with. There's going to be the presence of a horizontal asymptote. We can understand that this function can never be equal to 0, right? So as a result, y belongs to all real numbers, and y cannot equal 0. Okay? So having said that, we also understand that our restriction on our domain is going to be a vertical asymptote. However, we can understand that f of 4 here will give us 1 over 0, which is indicative of a horizontal asymptote. As long as you have c over 0, this tells you that you have, sorry, did I say horizontal asymptote? I meant vertical asymptote, right? If you have c over 0, this is indicative of a vertical asymptote. So we have a vertical asymptote at x is equal to 4. However, we don't have a vertical asymptote at x is equal to 2, right? Whenever you have 0 over 0, this is an indeterminate state, and as a result, we have a hole or a point discontinuity at x is equal to 2. Now, we want to figure out the equivalent y value. We know that f of 2 does not equal 1 over 2 minus 4. It wouldn't exist in the actual function. And that equivalent y value here is negative 1/2, right? So 2 and negative 1/2 will not exist, right? So the whole here is 2 and negative 1/2. Okay, so the whole will not exist, and we also have a horizontal asymptote at y is equal to 0. Okay, so keep that in mind. So using this, all of these things, we can kind of sketch a function. We're going to be looking at our simplified expression, sorry, a simplified function, and let's take a look at some of their intercepts. So because we said that the horizontal asymptote y is equal to 0, the graph won't cross our x-axis, right? So we don't have to look for x-intercepts. So we're just going to find a y-intercept, so I'm going to let x equal 0, so I'm going to do f of 0 here is equal to 1 over 0 minus 4, which is negative 1/4. Okay, so you get negative 1/4, so the point here is 0 and negative 1/4. Okay, so that's the y-intercept. And now what you want to do here is you want to plot these points, right? So we have a vertical asymptote, we have a hole, we have a horizontal asymptote, we have a y-intercept, and we can understand that this is a reciprocal function. So let's place our grid here, and let's sketch the graph. Okay, so looking at our grid, I'm going to place my vertical asymptote x is equal to 4. So let's place that here. Okay, so I'm just going to do the vertical asymptote in blue. Okay, so this is my vertical asymptote. X is equal to 4. We also have a horizontal asymptote y is equal to 0, so that's basically going to be the x-axis. Let's do that in red. So guys, use a ruler for this. Right, so this is our horizontal asymptote. Y is equal to 0. And we only have to plot our y-intercept, right? We have a hole at 2 and negative 1/2. So I'm just going to plot the hole really quickly. Let's do that in orange. So the hole here is 2 and negative 1/2. So 2 and negative 1/2. Let's say it's like somewhere here. Okay, well, it's going to be kind of hard to draw that out. Okay, so we're going to have a hole there, right? And we should have a point. The y-intercept is 0 and negative 1/4, right? So it's kind of hard to tell where this is on this grid. Okay, and if we follow the confines of the asymptotes, right, we're going to get something like that. Now this, once again guys, this is a sketch, so you want to have an actual idea of what the graph will look like. You should plot some test points. Okay, so yeah, I'm trying my best here to sketch this guy out, but right, so that's the idea. So this is one of our graphs, and the other graph here should kind of look like that. So you can do a series of test points. Alright, so that's our other graph here, right? And this hole, this point discontinuity of 2 and negative 1/2 does not exist. Okay, so that's basically it, right? So it's our rational function that doesn't, it has this hole here, it's a missing piece at 2 and negative 1/2, right? And if we wanted to look at our end behaviors, we could. So I'm just going to do my end behaviors out here in lime green. So if we're looking at our end behaviors, we can understand that if I'm going towards negative infinity here, right, as x approaches negative infinity, y will approach the horizontal asymptote from below, so 0 from below. As x approaches vertical asymptote from the left-hand side for negative, y also approaches negative infinity. And then in this case, as x approaches 4 from the right side, right, so as x approaches 4, the vertical asymptote from the right side, you can see that the trace in orange goes up, y goes to positive infinity, and as x approaches positive infinity, y will approach 0, or the horizontal asymptote from above. Okay, so this is the end behavior, and this is basically our a little spin-off of our example of point discontinuities or holes, right? You can see that we actually created a rational function, and this does take a little bit of time to kind of construct.